They said, would you like some music to kick off? I said, yeah, some 80s montage music will set the scene for this. As you can see, fairly retro-themed talk. I've seen some really beautiful slideshows today. I don't want you to underestimate the amount of effort required in making slides look this bad. So you're welcome. Yeah, with a clock, so I got timekeeping going on. Yeah, we'll see how that works out. So my name's Jonathan. I'm here to talk about embedded Rust and this crazy project I've been on for about 18 months called the Monotron, and we'll see what that's spiraled into. So first, some introductions. So you can find all of my code on GitHub, where I am the JPster. I tweet a lot these days, but I came to Twitter relatively late. So on Twitter, I am the real JPster, because somebody took the JPster before me. Don't ask that person Rust questions, because I'm pretty sure they can't help. You can find cryptographic proofs that prove I am who I say I am at Keybase, which is a great service. Recommend you check it out. And I belong to the Rust Embedded Working Group, and you can find all of the Embedded Working Group materials on GitHub/Rust Embedded. Check it out, some great stuff on there. We've got a number of books that are embedded related and a whole bunch of other materials, so have a look. So what are we going to talk about today? Well, this is a talk in 3 parts, I guess. So we're going to talk a little bit about embedded Rust and what makes embedded Rust different to normal Rust programming. We're going to talk about this project, which I built to sort of demonstrate embedded Rust and act as an example of what you can do. And then, fingers crossed, we might be able to put together a little demo for you. No promises. It's always a bit tricky with AV setups. As you'll see, what we've got here is pretty experimental, but we'll see what we can do. So I think you find that is the highest fidelity version of the Rust logo you'll see all day. So I came to the Rust project, it was around the 1.1, 1.2, I think. It's actually, I took a week off work with the flu, and I was stuck in bed and unable to move, and I had nothing to do, and watched all the TV I could manage. So someone at work had been going on about this language and said, it's interesting, it does good stuff. And within a couple of days, having never picked up the language before, I'd written a functional web server that could sort of parse HTTP requests. And I was like, okay, yeah. Now, as a professional C programmer, I was sort of falling over these foot guns all the time, all these things that are really easy to get wrong. And I'd spent a lot of my professional life building up these processes to deal with these things that are really easy to get wrong. And suddenly there's a language that's like, no, we've taken care of that for you. You can go and concentrate on the more interesting aspects of programming. And so, fell completely in love with the language, and I've been getting more and more involved in the embedded side. So the Embedded Working Group, again, I think you agree that's a great quality logo. Incidentally, there is a tool you can download called RexPaint. It is an ASCII art painting tool. Your palette of brushes is basically the set of ASCII characters, and then you can draw with them and do lines and rectangles and so on. It's a real time sink, so if you're like me, maybe avoid that. So the Rust Embedded Working Group formed, maybe about 2 years ago, I can't remember now. And it started out with about 5 or 6 of us, and we'd get together once a week or every so often just to chat about what we've been working on. And it's spiraled, especially with the Rust 2018 release. We put a lot of effort into making embedded Rust work on stable on a number of different targets. And now I think there's well over 100 people involved. We get together once a week on a Tuesday, and we chat on Matrix. Recently had to switch from IRC to Matrix, so there's a whole bunch of fun for you. We've written a bunch of support crates for the different boards, which I'll talk about. We've written a couple of books. One is an introduction to embedded systems that happens to use Rust, and one is a book for people who already know embedded systems, and it teaches them the Rust-specific bits. And then there's a third book called the Embedonomicon, which is all the deep, dark, and scary bits of Rust we've written, so you don't have to that actually get these chips to boot in the absence of an operating system. As I said, it's all their stuff's on GitHub, so check it out. So if you want to do embedded Rust, what do you need? And what do I mean by embedded Rust? So I mean you're running on a platform that doesn't have an operating system. You could say that running Rust on a Raspberry Pi is embedded, and for some people that is a resource-constrained platform, but I think when I talk about embedded Rust, you're talking about systems that don't have an operating system, or if they do, it's a really simple RTOS, and they've got memory measured in the kilobytes rather than the megabytes. So if you want to write some embedded Rust code for a specific chip, and there are an awful lot of chips out there, you need a few things. So first of all, you need LLVM to be able to generate machine code for your target. It has a bunch of CPU architectures built in, and there are more being added. So we're aware there's a fork for the Atmel AVR series. So what happened was somebody took LLVM and they forked it to add AVR support, and then the Rust team took LLVM and forked it for their thing, and then someone just needs to like zip the two forks together, and that's a work in progress. But there are a number of platforms where the support is all sorted out. So once you've got an LLVM backend, you have to tell rustc, which will then tell LLVM how to generate code. Just because it knows how to generate, I don't know, for example, x86 machine code, that's not enough. You need to know the rules about how big the integers should be and how much stack space you allocate in various places. So that's a thing called a target file. You can supply your own. If you're on an experimental platform, you might find someone has a .json file in the tree, and that contains all of the information, but eventually that will get merged into the compiler source code, and it becomes a built-in target. The next thing you need, really, is a pre-compiled libcore. Core is the subset of standard. We can't run standard because we don't have an operating system. We don't have threads and file systems and all that nice stuff. So we're stuck with core, which is sort of the basic subset. You can compile your own core, but as far as I know, it's still the case that compiling core requires nightly, which is not ideal. If you're trying to build a stable system, using the stable compiler is better. So the solution was to ship pre-compiled core libraries. So if you use rustup target list, it will show you a whole bunch of targets where you've got pre-compiled standard libraries. If you search for the word none in there, that shows you the embedded ones. And we've got Cortex-M, ARM Cortex-M, ARM Cortex-R, and some RISC-V 32 and 64-bit platforms in there at the moment. So those binaries are pre-compiled and they're shipped out to everyone through rustup. So getting set up for a sort of a standard Cortex-M system is super simple. You just need rustup, and then that can pull in everything else you need. So let's have a look at an example of why I think Rust is really powerful on microcontrollers. The classic example is you're doing, you need to disable interrupts to perform some operation. Perhaps you've got some shared mutable state. That stuff we all think is really scary. Well, it turns out embedded hardware is just a giant ball of mutable shared state. It's just what it is. So yeah, you need to disable interrupts. In C, you might have a function, disable interrupts. I'm going to do a bunch of stuff. I'm going to turn the interrupts back on again afterwards. It's really easy to return early and then never get to the re-enable line at the bottom. Or you could forget to re-enable, the compiler won't check that you've got the right calls in. Well, we can use closures. You don't need an operating system to use a closure. So here we've got a function called free, and it operates, it executes some function f in an interrupt-free environment. So it's going to disable interrupts with the primask module. So we're going to get the current interrupt state with primask. We're going to disable. We're going to call our closure, giving it this magic critical section object. The critical section object basically acts as a proof that you are in a state where interrupts have been disabled. Stops people calling functions outside of that state. That's an unsafe thing to create, where unsafe means, don't worry, compiler, I've got this. That would be a fairly lengthy keyword, if I'm honest, so I can see why they went with unsafe. But yeah, you say to the compiler, don't worry, I've got this, make me a critical section because I know I've got interrupts disabled. And no matter what happens in function f, if it returns early, whatever, it doesn't like its arguments, you will always re-enable the interrupts afterwards. So there's a whole bunch of stuff now I don't have to worry about. I don't have to worry that I've got these things matched up, and that's super powerful. So another example, doing memory mapped I/O. The cute thing here, So this is for an object called a cache and branch predictor. Embedded systems are full of really, really forgettable names. So the CBP is the cache and branch predictor. The important thing is this struct is zero-sized, and then the address of the peripheral in memory is produced through the deref system. So so it's really efficient, and then the compiler just inlines a whole bunch of stuff. But basically, I'm saying we can access the hardware, the serial ports, the low-level stuff in the chip. We can access it in a nice fashion. So the projects you work on are just sort of built in a stack. So at the top, there's the thing you're writing, the application, the game, the little widget demo, whatever it is. So that sits at the top, and underneath you've probably got what we call a board support package. So this will be a crate someone has written that describes the board you're running on. It might be a commercial board you can buy, maybe an ST Micro discovery board. There'll be a crate that says, okay, I've got 3 LEDs and I've got 2 buttons, and you can call button1.isPressed, returns a true or a false. So basically just sets up a bunch of stuff related to how your board is configured, which pins are connected to which interesting things. Below that, we have a hardware abstraction layer. So the embedded working group have put a lot of effort into making, for example, an ST Micro serial port look and feel like a Texas Instruments serial port, or maybe a serial port on your Linux laptop. These serial ports all do the same thing, but at the hardware level, they look very different. And in C, it's very tricky to come up with a uniform implementation. You end up in very vendor-specific places. So here we've said, no, we're going to have a standard implementation of a serial port as a trait. You can read a byte, you can write a byte. And then if we implement that for a whole bunch of different chips, your code is now portable. You can run it on ST Micro, you can run it on Texas Instruments. And that's what the hardware abstraction layer is about. And then below that, we have some auto-generated code. We can take manufacturer definition files that say, we have a UART peripheral here. It has these registers at these addresses with these fields, and these fields have these meanings. There's a lot of stuff to read in the datasheet. I mean, I've seen datasheets that are 5,000 pages long, and to convert that into Rust code is pretty tedious to do it by hand. The files we get aren't perfect, but it's a pretty good start, and so we auto-generate this sort of access layer, which is how we get to the hardware. And then finally, you need something for the specific architecture. So these chips have a process by which they boot up and start running, and we've got code, certainly for Cortex-M and Cortex-R, that do that for you, so you don't have to worry. So that's sort of the bottom layer. Right, so let's talk about this project I've been working on. Some of you may remember the Commodore 64. Yeah, I'm just about old enough to remember that. Yeah, a bit of BASIC. You never thought you'd come to a Rust conference and see BASIC up on the slides. So this is where I got into embedded computing. I had my Commodore 64. I was terrible at playing games, so I'd plug stuff in the little connector at the back, and I'd write peaks and pokes that we could turn motors on and do that stuff. So that's where I love this sort of interactivity, where I do a thing and then physical, real stuff happens. And recently, sort of last year, I wasn't enjoying my job. I wanted a side project. I was really getting into Rust. And I thought, well, maybe I can recreate some of that sort of 1980s experience of having a really limited platform. And I think there's a lot of art to be found in extracting a lot from very little. So what did I want to do? Well, yeah, I needed this distraction. The challenge I set myself was, can I generate video? Can I get a picture up on a monitor using a microcontroller that's not designed to do that? And then, if I can do that, how much more can you get in? What can you get out of one of these tiny processors? So the first board I looked at was, that's a wonderful photograph, I think you'll agree, is a board called the STM32F7 Discovery. Again, we're great at naming things in the embedded world. But this board comes with like a 4-inch LCD on the front, and you get a fairly powerful processor, runs at a couple of hundred megahertz. I could have done the project on this board, it would have worked, but it already came with a screen. So generating video is like a solved problem. It's got built-in video accelerators that do this work for me. And yeah, sure, using them would have been interesting, but it's too easy. So I use this board instead. This is the Texas Instruments TIVA-C Launchpad. It's quite nice because it contains 2 processors. The one at the top does USB serial conversion and is a flash programmer and JTAG tool. So you can just plug it in via USB, and that's all you need to reprogram the board. And then the top chip actually reprograms the chip in the middle. We've got a Cortex-M that runs at 80 megahertz. We've got 256K of flash, and we've got 32K of RAM. And that's it. So that is incidentally not enough RAM to hold an entire picture at a resolution that you're looking at up on the screen. So what can we do? So to generate analog video, how does this work? Well, in the olden days, you had electron guns, and yeah, in the olden days, when kids watched TV, they sat in front of a particle accelerator which fired electrons at their face and made special chemicals glow. Kids these days don't believe it. But this electron gun swings from left to right, lighting up the screen as it goes. And that's basically how the video signal works. You generate a picture by sending each horizontal line. You need to get the timing correct. The pixels are sent out from left to right. Then there's a bit of a gap while you wait for the gun to move back to the other side of the screen. And then you've got these sort of blanking areas at the bottom and the side. So when it comes to generating VGA video, and I went with VGA because, which you'll see as the numbers work out a bit nicer, but VGA monitors are kind of easier to come by. Like I can feed VGA into systems like this. It's an amazing website, you should check it out, called Tiny VGA. It's really good. So there's a bunch of different standards, a different set of resolutions that are specified. The standard VGA resolution, 64480, is 25.175 megahertz. I've got an 80 megahertz clock. That is not going to divide out. There is no number no integer I can divide 80 by to get 25.175. That's going to be a nightmare. Standard BIOS text mode, or the text mode you use in DOS, turns out is this resolution, 72400. Yeah, no, that's a bad number. I'm not going to be able to generate that. So I kept going through the list. The next one, 800 by 600 at 60 hertz, turns out to use a pixel clock of 40 megahertz. That is, there are 40 million pixels generated per second, and if you can generate them at that rate, you will generate a signal that any standard VGA monitor will connect to. And so that's the system I built. Now I said before we're using VGA. Well, VGA is a color standard. In mono world, you just basically send a voltage to the monitor, and the bigger the voltage, the brighter the dot, and that goes you from black to white. And then there's a little period on the left where it goes negative for a little while, and that just tells the monitor where the edges are, so it knows how to line the picture up. In color world, we have a red channel, a green channel, and a blue channel. And then by mixing those together, if you have analog levels, maybe 8 bits for each, that's where you get your 24-bit color from. In my world, I'll be lucky if I could just turn them on or off, which gives me about 8 choices of color. But that's what we have to do. And then because I said we don't have enough RAM to generate the picture, what we're going to need to do is store basically a font which has on or off, so you have your pixels on or off, and then call it maybe foreground and background, and then I can pick 2 colors. So I could set my foreground to green and my background to black, and it would look like this. But if I set my foreground to white, my background to blue, it would look different. So then all I need to store in memory is just, I'm using a copyright character at this location, and I want it blue and white, or black and green. And that uses much, much less memory than trying to store the color of every single pixel in RAM, because we haven't got enough RAM for that. The downside is, as the screen gets drawn, I have to look up the character in the font and then apply the color transformation to color all the pixels and then get the pixels chucked out. I actually run the video at half speed, so I'm only running at 20 megahertz, but that does mean I only have 4 clock cycles per pixel. That's quite a lot of work to do to get each pixel sent out of this system in only 4 clock cycles. So it's a fairly tall order. So it's not a terribly readable example, I get that, but basically we're just saying I have my array of characters and colors in a line. I can iterate through that. I have to do some funky pointer arithmetic because I can't afford the bounds check because I've only got 4 clock cycles per pixel. So there's a bit of funky pointer arithmetic in there. But spoilers, this works. this code will run fast enough on this chip to generate actual video. The color lookup, it turns out if you do it as like a match or some kind of statement like that, or a bunch of if statements, it takes way too long. The solution, and it took a long while to work this out, the solution is to blow 25% of my flash space on a massive color lookup table. So I take the 8 bits I want to color, and then the 2 colors I've chosen, well, that gives me 14 bits in total. Well, that's a table with 16,000 entries in it, and each entry is the red set of pixels, the green set of pixels, and the blue set of pixels, and some padding. So it takes up 64K, but it means I can go from foreground and background color to red, green, and blue in only a couple of clock cycles, which is really powerful. Without that, so the reason it's called the Monotron was because for ages it only did black and white. I guess I should rename it now, but yeah, we can do color. Interesting problem with the timing. If you don't get the red, green, and the blue completely aligned, you get these sort of weird fringing effects. It's actually impossible to get this CPU to start the red, the green, and the blue simultaneously. I'm using a special peripheral here called the SPI bus. I'm using 3 of them. You can't start them at the same time. They need different memory writes, and it's impossible to do 2 memory writes at the same time. And for ages, this stumped me. It turns out what you can do is you start the red channel early, and then you use a bunch of no-ops to just slow the processor down just enough until the exact moment you've transmitted 8 bits of red, and then you can start the green, and then you have a bunch more no-ops, and then you can start the blue, and then it all ends up in phase. Yeah, that took some doing. So how does the memory layout look? Well, I've got a flash ROM. I think of that as sort of a ROM in a sort of typical home computer sense, and I've got RAM, and you get the various sections. It's just like compiling code for any other platform, really. You know, if you were writing C code, you'd be familiar with all of these sections. The data section gets copied from flash to RAM on startup. Got my interrupt vectors at the bottom. So once I got this system, I thought, well, I mean, it's fine. I can make pretty pictures appear, but I wish it was a computer I could use. I want to be able to install applications. I want to load an application in, use it, and then when I turn the computer off and on again, the application's gone, because you know that's how these systems I like from the 80s tended to work. But to get your application to talk to this sort of ROM and this sort of kernel I built, you need an interface. So the system I designed was basically when you load a program into RAM, you get the top 24K to play with. The bottom 8K belongs to the system. The first word in your application space should be a function pointer. And then if you put your code in RAM, the kernel will look at that, treat it as a function pointer, and jump to it. Don't care what you do with the rest of the RAM. That's your business. But what I will give you is a structure full of function pointers. And those function pointers are how your application can ask the kernel to do things like draw on the screen or various other operations. And then I've spent a long time thinking about what should these sort of system calls look like. I think maybe they should look like CPM, maybe they should look like MS-DOS, maybe they should look like POSIX. I haven't really got a good answer for that. They're sort of a bit of a mismatch at the moment. But we can do things like, has anyone pressed a key on the keyboard? So you can connect up maybe a serial interface and you could type some text into your computer. Wait for vertical blank interval, so that's wait till the screen is finished redrawing, because if you try and draw on the screen, if you try and modify the contents of screen memory while it's drawing, you get sort of weird tearing effect. So it's probably best to wait to the bottom of the screen before you update a bunch of stuff. Maybe if you had font support, you could change fonts, that sort of thing. Wouldn't it be cool if it had a joystick interface? Yeah, because then you could play like simple games. Would be interesting. So that's sort of the project in a nutshell. I can say at this point there is a PCB. I've got one here. You can grab me in the hallway track and have a look. It started out as a bit variable, it was a bit unreliable, so there is a PCB. There's going to be a Rev 2 because it has bugs, but it's got serial ports on it. It's got a clock. I've used a clock in the slide here to show that off. So what else we got? We've got a printer port. Wouldn't that be interesting? If you could print, there's a printer port on the PCB. Haven't worked out how to make it work yet. I need to go and do some research on how the hell printers work. And there's some more. Right, so that's the end of the slides. Who wants to see a demo? Okay, so I did say that making slides look this bad is remarkably difficult. I'm going to be honest with you. The laptop is still in the bag. The computer itself is. So we've got a computer to play with, and I've got about 5 minutes, and I've lost my clock, so I'm probably going to run over, and I apologize in advance. So, wouldn't it be fun if we had a disk drive so we could load programs? We have a disk drive with FAT16, FAT32 support. I can read from an SD card. I can just pull the card out, shove it in the laptop. I've got programs on disk that I can load into RAM and then execute. So if you want to, I don't know, maybe you want to do some programming, so we can deload tinybaz.bin, run. We have basic. So this is basic for the 68,000. It's a C program. I managed to hook the C program up with my Rust crate that contains all of my system calls. So yeah, we can do, you know, it's got to be done. I can't bring up a basic program and not type this. So you know, there's that. So the screen is redrawing every line. There are 37,500 lines per second, effectively. If you take the 60 hertz, times it by the 600 plus the blanking interval, well, it's a tiny bit of CPU left at the end of the line. Maybe you could get it to, I don't know, generate a beep. That'd be interesting, wouldn't it? Maybe, in fact, you could use the MIDI interface. So I apologize because I'm not a musician, but I do happen to have a MIDI keyboard with me. So if you are a musician, feel free to come and grab me later. We can set this up with a little set of speakers. As I say, I can't really play music, but you know, we can do that. What else have we got? We've got a joystick. So maybe to finish up, we're going to play a little game. Some of you have seen it up there. Before we go into that, you're about to see an effect in the title screen. I just want to explain a little bit about how that works. When I'm drawing the video lines, I have to work out what's on each line of text based on where I am on the screen. It turns out just because you're in line 300 doesn't mean you have to draw the pixels that should be on line 300. You can in fact have a little mapping table inserted in the front which allows you to move any line to anywhere else on the screen, which lets you do this kind of effect, which is kind of fun. So you can see how this sort of thing might be useful for sort of scrolling backgrounds or things like that. So let's fire this up. So this might be loud, so I'm just going to warn the AV guy. Run. Yeah. I was really impressed with this tune because I wrote it on an airplane by typing in the frequencies into the source code, and then afterwards my wife said, "Why does your computer keep playing Bob the Builder, classic British kids TV show?" It's like, oh yeah, it seemed familiar. So to finish up, I'm going to have a quick bash on Snake. Every time I eat an apple, I would like you to whoop and cheer because it's really not very easy. And then when I eventually come to my terminal demise and eat my own tail, that will be the end of it. So thank you very much. Let's give this a go. All right. Right, let's play on here. Oh. Yeah, come on. 10 points. The more So the more I eat, the faster it goes. So we really won't be here all day, don't worry. Uh-oh. Oh! Yeah, we're getting quicker. Uh-oh. Ah, there we go. Thank you very much, everyone. Thank you.